Hello, welcome back, physics students. So today we are talking about conservation of energy. So we played around with a skateboarding interactive, and we noticed that the total mechanical energy of the system was not changing. Now that's pretty crazy. And so we're going to talk about something called an isolated system. So if we have an isolated system, so if I put a bubble around my skateboarder and the earth, and that is my system, then if nothing comes in or out of that bubble, we consider that an isolated system. So nothing is interacting with the objects inside the bubble. It's just those objects, and they can interact with each other in different ways, but nothing else is coming in or out of the bubble. And so that's an isolated system, and that's when we're going to have this thing called conservation of energy. Energy is only conserved in an isolated system, so when nothing punctures the bubble, nothing comes in or out. Okay? And so we saw that the relationship between the objects could change. So the skateboarder can get closer to the earth, and so his height is changing and his potential energy is decreasing. But if you notice, then his kinetic energy at that same time was increasing. And so all of that lost potential energy became kinetic energy and it stayed within the system. The energy didn't leave the system. All right. You also notice that there was no thermal energy. Thermal energy would be how energy is leaving the system of skateboarder and earth. And thermal energy would be taking some energy out using friction and putting it into heating the ramp. And the ramp is not part of our system at this point. All right. So in the real world, in a real skate park, you would not see that this person going up and down the half pipe, right? You wouldn't see them continuously reaching the top. Eventually, they would slow down until they no longer reached the top of the ramp. And so that's what happens when we put friction into our system, and when friction is taking energy away from the objects that are interacting. So today we're just going to be continuing talking about just an isolated system. And so the following is how we would deal with the energy throughout the system as it changes from an initial state to a final state. The really cool thing about energy is that we don't care how an object moved. We only care about where did it start, where does it end. The journey is not the important part with energy. When we were talking about velocity and acceleration, right, the journey was everything. But with energy, the journey is just a means to an end, and we care about where does it start, where does it end up. All right, so without further ado, let's jump into conservation of energy bar charts. All right, so how are we going to use these energy conservation bar charts when energy is being conserved from the initial to the final state of the object? So first we're going to need to identify our system. And so I'm using our simulation here, and I'm going to put a little bubble around my system. And so my system is going to consist of my person on their skateboard and the earth. Everything else is not part of my system. So the track is not part of my system, the air is not part of my system, etc. All right, and so then over on the right, where it says initial energy, above this initial state, I'm just going to kind of extend my line here. This is my initial versus my final, right? And in between there's something called energy transfer. If energy is being conserved throughout the system, there is going to be no work or energy transfer. So there's nothing coming into or out of the system, and so that means there's going to be nothing there, and so we're going to get rid of this section of our chart. We're not going to use it yet. In the future, there will be things coming in and out of the system, and that's when we're going to start using that. So our initial system, we're going to have our earth. Earth is always part of the system, so always include earth in your system. And then we're also going to have our skateboarder, and he is going to start up here somewhere. All right. And our skateboarder is going to be at a height of 6 meters above the ground. All right. And then afterwards, we are still going to have the earth. And now we're going to talk about maybe our skateboarder is down here on the other side of the turnpike, and he is now only 1 meter above the earth. All right, so his height changed However, the two objects within the system are still the same, skateboarder and Earth. At the beginning, we're also going to give him a velocity of 0 meters per second, and at the end, we don't know how fast our skateboarder is going. It's got some speed, but we're not entirely sure what that is. All right. So now we're going to go ahead and use our conservation of energy bar charts. So the initial energy, we're going to talk about energy is kinetic plus potential. We have no work, right? So then we're skipping the energy transfer, equals the kinetic plus the potential. Notice I'm putting an F for final energy, and I'm going to add an I for initial energy. All right, at the beginning, we know that our skateboarder is not moving, 0 velocity, and so they're going to have 0 joules of kinetic energy. And then we know that they are 6 meters up, and so that is going to give us some potential energy. All right. So we don't exactly know how much that is, but it's 1, 2, 3, 4 bars, okay? Again, it doesn't necessarily matter how many bars as long as we're making sure it's conserved throughout. All right, so we went from 4 bars of potential energy. Now we're only down at 1 meter tall. And so we're going to have some less potential energy. I'm going to go with 1 bar, which means I still have 3 bars left. And that energy has to go somewhere, and so I'm going to say that's my kinetic energy. Okay, so now this is still 4 bars total for over here, and 3 plus 1 is 4 bars total. All right, so now what I could do is I can go ahead and I can actually calculate how much energy I had before and after the skater dropped down the turnpike. And so for my initial energy, it's only potential energy. So potential energy initial, I'm taking out anything that ended up being 0 joules, is equal to my kinetic energy afterwards plus that potential energy afterwards. All right, and so now since I don't actually know those values, I'm going to go ahead and substitute in our equations. So we know potential energy is mass times gravity times height, and we know kinetic energy is 1/2 mass velocity squared, and potential energy is mass times gravity times height, okay? And so because there is no work, there is no energy coming in or out of the bubble is staying intact, I can write out this statement, okay? And now I can go ahead and I could actually solve for what I don't know. And so I know the heights, I know gravity, I don't know this velocity, and I'm curious, how fast is he going at the end when he's only 1 meter above the earth, okay? And so something really cool that I can do is I can say there is a mass here, a mass here, and a mass here. So since there's mass in all 3 pieces, right, a different piece is separated either by an equal sign, an addition sign, or if there had been subtraction. Those are different pieces. And so since there's an M in all of my pieces, I can go ahead and get rid of this. And I can rewrite my equation. Gravity times height equals 1/2 times velocity squared plus gravity times height. So now I can't actually calculate my total energy. However, I can go ahead and find that missing velocity value, and I can know how fast my object was going after he dropped 5 meters. And so we know gravity is always going to be 9.8 meters per second squared. Height, I'm going to go back up and look. Oh, we were 6 meters above the earth here. 1/2 is a constant, so that's going to stay there. Velocity squared. And then again, 9.8 meters per second squared for gravity. And I can look above and see, oh, we are now 1 meter above the earth. All right, so I've got all my numbers in there, and I can go ahead and I can calculate, and I can actually find that velocity value. And so I'm going to say 9.8 times 6 is going to give me 58.8 meters squared over second squared, which is equal to 1/2 times velocity squared plus that 9.8 times 1 is going to give me 9.8 meters squared over second squared. All right, now I'm going to go ahead and I'm going to subtract out this value, so minus 9.8 meters squared over seconds squared. Notice that my units ended up being the same, and that's why I am able to subtract that to the other side and combine those terms. And so that is going to go ahead and give me 49 meters squared over seconds squared. And that is equal to 1/2 times velocity squared. I'm going to go ahead and I'm going to multiply everything by 2. And so I end up with 98 meters squared over seconds squared equals velocity squared. And then I'm just going to square root that number. And that square root ends up giving me approximately 9.9 meters over seconds for velocity. And so here I was able to find the velocity of the object without actually knowing the actual total energies, just based on what I already knew about the height and that energy is going to be conserved because nothing is breaking the bubble for this object. All right, so now what I'd like you to do is I would love for you to go up here, go ahead and create those energy changes. So I've given you some values. Go ahead and create some changes there. Show me what is happening, and then go ahead and calculate those missing values.